We're on to the second part of the review. We have the definitions and theory questions, and the first one is a definition of the derivative. So let's figure this out. And, well, let's write it out over here. So the derivative at a particular point. So the notation for that is f prime evaluated at c. That brings you to the particular point. And that's equal to the limit as h approaches 0 of f of c plus h minus f of c divided by h. Now this is exactly coming from your derivative f prime of x is equal to limit as h approaches 0 of f of x plus h minus f of x all over h. Now instead, though, you replace this thing with c, so every time you see an x you replace it with c, and that's exactly what happens here. Okay, so that is our definition. Now the next two problems, the geometric interpretation. Let's just say that the derivative is the same thing as having the slope of the tangent line at the point x equals c. Actually the point is c comma f of c, but saying x equals c implies that this is your point. Physical interpretation for the derivative at some time t, this is the same thing as the velocity. Velocity of the particle. Okay? And then the next one is using the definition of the derivative to find dy dx. So this is the definition. We'll come back to this definition because this says to do it for x. So let's write dy dx, which is also f prime of x. And notice that this is x now, not c. So I'll use the original derivative definition. Limit as h approaches 0 of f of x plus h minus f of x all over h. So this becomes a limit problem. Limit as h approaches 0. Now f of x plus h. And wherever I see an x in this function, I'm going to replace it with x plus h. And let's start off by using placeholders. So that's this first part. The second part is f of x, which is just exactly what this thing says. X squared plus 2x minus 7 all over h. So back to this first expression, x plus h, x plus h. So we have not taken the limit yet, so we'll keep this limit symbol here. Now the first one gets FOILed out. This is x squared plus 2xh plus h squared. That's the very first term. We have a 2x plus 2h after distributing the 2 and a minus 7. Now this looks like I can just lift the parentheses and then distribute the negative sign. So I'll start off with an x squared negative, 2x negative, and then the negative 7 becomes a plus 7 after that got distributed. H in the bottom. Now let's see things go away, like the negative x squared and the positive x squared. A negative 2x and a positive 2x. And a positive 7 and a negative 7. So what we have left has h's in them. So I'll do this in 2 steps. First, we'll factor out the h from the numerator because every single one has an h. So we got 2x plus h plus 2 after getting the h, and then now the h's cancel. limit as h approaches 0 of 2x plus h plus 2. So let's send h to 0. There's only one h, and that goes to 0. And so what we have left, we've finally taken the limit, so what we have left is 2x plus 2. And that's our derivative. Okay, this next one we actually did in class, but let's do it again anyways. I told you that the f here is not important, and we didn't really talk about the second derivative, so let me just put pluses here because all the y values of every single one of these points are above the x-axis. So being that they're above the x-axis, that means that they're positive. Now the derivative, on the other hand, is not looking at the place of these points, but rather looking at the tangent line of those points. So let's look at A. If you were to draw a tangent line, you'll see that the tangent line has a positive slope, so that's going to be positive. B, if you were to draw the slope right at B, it looks like it bounces from being a negative slope to a positive slope and goes down and goes up. So at this exact point, you have a slope of 0. That line, that tangent line that was drawn there, has a slope of 0. So you can say that it has 0 slope. C, from left to right, looks like it's going down, so it's a negative slope. D also looks fairly negative, and E looks like it might have flattened out right there, so it'll have a 0 slope. So f prime, remember, geometrically, is looking at the slope of the tangent line. So what we're doing is we're following the slope of the line. Here we have two examples. Again, this was done in class. And we actually had a worksheet that had more information about that, and solutions are online, so feel free to look at them. Alright, let's take a look at this one. So when we're asked to graph the derivative on the same set of axes, what you can imagine doing is take some points, sometimes randomly, sometimes not so randomly. This is probably the time where you can just randomly pick points and look at the tangent line. And whatever the value of the slope of the tangent line is will be the value of the derivative. Now, I don't know the exact value of these tangent lines, but they're all the same. And they're all negative. So again, not knowing the value of the tangent line, and if I were just to pick a negative value, negative, same value, I can just draw a line down here that's horizontal that gives me all the same values, and it's all negative because it's all below the x-axis. So this would be your derivative for this problem. Now for a more interesting curve that looks like this, what would be interesting to find out are where the slopes are 0. So I would probably first identify the 0 slopes on the graph. And that would ensure that my derivative would have a value of 0. So I know my derivative will be passing through these points. Now before this point over here, my graph is increasing. It starts off kind of steep here, and then it gets less and less steep and goes down to 0. Increasing, when the graph is increasing, that means these are all positive values. So it starts off kind of high here, positive, and here it gets not so steep anymore, so it goes down. So we'll be looking at following these points until you get to that zero slope. After you hit that first zero slope, you'll see that the graph now becomes decreasing. Now decreasing, the slope of these arrows over here look like it'll be negative, and then maybe right at this point it's at the steepest. After that it's still decreasing, but it's not so steep anymore. So until it reaches here where you get close to zero, until you eventually get that zero slope. So maybe the graph just comes back down here until it hits that zero slope. After that your slope is increasing again, so it looks like it'll be going up again. So at least for this piece of the graph, I can see that this derivative would probably look something like this. This is your y prime. Alright, I encourage you to practice these types of problems using the worksheet that we had from this last week, and see how you do. Also a bunch of homework problems and some problems in the book. This one is an analytic approach or symbolic approach to looking at continuity, and it's also looking at differentiability. So let's see, we have a graph that's broken up at 1, it looks like. So 1, we have a special point. Before that we have a line, it looks like it crosses here at 3. And then the slope C, we don't know what the slope is. Oops, didn't cross at 3. So the slope, depending on what C is equal to, could be steep or not. And then we have a point K at 1. Now that point K could somehow be randomly placed over here, but depending on what value we assign to K, we can make it land right on that point if we wanted to. And our third piece of the graph is 7 minus c times x squared. Now 7's all the way up here, but we're not going to care about what happens before 1. What we are going to care about is what happens after 1. So probably this piece of the graph. Now this is an open circle. This is an open circle. And what we want to do is we want to make it so that these two graphs coincide. So let's see what happens. Find the value of c so that the limit exists. So the limit has to exist if the value coming from one side is the same as the value coming from the other side. So limit as x approaches 1 from the negative side of your function. According to the piecewise function, this limit is going to be approaching 1 from the negative side. Negative side means all values less than 1, so it means we're going to be using c x plus 3. And if you don't have any issues with fractions or anything that would give you a 0 over 0, remember all you're doing is really just plugging 1 in. So put 1 in for x, and then you get c plus 3. Alright, so we still don't know what c is equal to, but we know the limit coming from the left side should be c plus 3. Now the limit coming from the right side, limit as x approaches 1 from the positive side of the function, will be limit as x approaches 1 from the positive side of this function, since this is the positive side. So that's 7 minus c times x squared. And again, there's no issues with fractions, so I'm going to put 1 in for x. So this is 7 minus c times 1 squared, which is 7 minus c. Now I think if we just set these two things equal to each other, we should be able to solve for c. So if I add c to both sides, you get 2c is equal to, subtract the 3 from both sides, you get 4. So c is equal to 2. So if we let c equal to 2, these two things will end up reaching 2. I guess the value 2, well, we don't know what the value of 2, we don't know what this is yet. All we know is c is equal to 2. Now, we are interested in this value because we want to make it continuous, and to make it continuous, this is a k, remember. When x is equal to 1, k is going to be, oh, what if we make k equal to whatever this number is? And how are we going to know that number? Well, when c is equal to 2, we get c plus 3 is 2 plus 3, which is 5, or 7 minus c, taking the second equation, is equal to 7 minus 2, which is equal to 5. And we better get the same number because we set those two things equal to each other. So we're going to want our k to equal to 5 so that they have the same y value, and now those two graphs will meet. This hole will be filled in, and so this will be continuous. So I think our graph is all set up. We did the graph while we were figuring out the problem, and this is how it would look like. The last one, it says, is f differentiable at 1? Well, one way to look at differentiability is that differentiable should mean looking at the smooth curve. Now clearly this is a corner, so by looking at the graph it doesn't look like it's differentiable. But we can also be analytic about it. We can do that by taking the derivative of this, taking the derivative of that, and at 1 it should be the same. And since at this point we haven't really taken too many derivatives yet, we're going to do that in great detail in chapter 3. I'll just leave it as is and say because it's a corner, it's not differentiable. Okay, so that's it for the review. Look through the web page online that talks about the review, and make sure you prepare for all the different types of questions. Also take advantage of your SI. She's making herself available, so I hope you all respond. Okay, good luck on the test.